Hello, everyone. Welcome to another concept. Now we are doing equilibrium, static equilibrium, and stress and strain in solids. Now we are going to look at fluid. Specifically, we're going to look at liquid. Today we're going to talk about when the fluid is static, meaning it's not flowing, and then in a later chapter we're going to look at what happens when fluid is flowing. You have to be very careful about fluid flowing and fluid not flowing. The situation is dramatically different. Okay, so here is a fluid not flowing situation, and a fundamental concept of fluid not flowing situation is pressure. And we when fluid is static, we say pressure is static pressure. So this is also called static pressure. But there is nothing static about pressure, but it's just given the name static pressure, the pressure that you would encounter if the fluid is static. Okay. Now, what is pressure? So we got to know what is pressure to answer this question. And once you know what is pressure, we have several ways you can answer this question. So the pressure is a name for bulk stress. Bulk stress, meaning stress. So stress at a point. So if suppose I have for fluid you need a container, and this container, and fluid flows freely, so container will become flat, and gravity is this way. So it's static after it stopped flowing. So if I look at some point here, so what's the stress, bulk stress here? So to get the bulk stress here, you will say, if I were to look at a small element, and when there is nothing around, no pressure, it has one shape, and then if it's pressure, it may shrink. So the amount of volume shrink is delta V. So pressure is being applied equally. Unlike stress in a solid, the solid may have a different stress in different direction, but in fluid, because it can flow freely, all of this stress in any direction will be the same. So delta V over whatever the V, and you have a bulk modulus. So this is the amount of change, and bulk modulus is stress, which would be here same as pressure. So another way to look at stress is, if I look at a unit area, so if I look at the top maybe, so you look at a unit area, so look at something like that. So unit area, and we erase this. So look at a very tiny amount. You have a unit area. So this is some area A, and you will have pressure from top and bottom. They will be equal to each other, right? If it's in static. So unit area, how much force is acting on the unit area? So this will also be equal to force acting over area perpendicular to that force, to this force. So take an area, and all this force is acting. So in a fluid, to answer this question, we will need to figure out how much force is acting. So let's look at a what happens. So this is a fluid, and fluid is assumed that this is open to air. So this is air and this is water, and we are at 200 meter. So if you look at a area, weight of this much water and all the air, all of this weight, so you have a weight of air plus you have a height h and area A, weight of water. All of this is acting on this area. So the pressure at this point, pressure here should equal to a weight of air plus weight of water above this water over the area A. And if I were given some kind of deformation over here, I can use this, but it's not given. The volume change is not given, so you don't really go that direction. You can go this direction just from the definition of stress. This is just a definition of stress, and this direction is the Hooke's law for. So you can use either direction in a problem situation. Okay, here we can W air over A plus W water over A. This is called atmospheric pressure. And this value is like 1.0 times 10 to the power 5 Pascal. And so this one will be M. Mass of this will be density of water times the volume. Volume will be area times the height times G. So this is the mass, and you can see the area cancelled out. So the answer for 1 will be use the density of water, that's here, and this is seawater, so we'll be use this density of water, and then the height is 200 meters, and the G will use a 9.8. So this should be 1.0 times 10 to the power 5 plus density is 1.02 times 10 to the power 3, height is 200 times let's use 10, and so we have 1.0 times 10 to the power 5 and a 2 times 2.04 times 10 to the power 3, 5 and 6. So actually the water part is almost twice, 20 times this. So this is equal to it just goes over the decimal here, so like 2.14 times 10 to the power 6 Pascal. So 200 meter, you have almost 20 times atmospheric pressure down there, unless I made some kind of calculational error here. All right, just to recap, this situation is static pressure at there. So we are looking for some way we can figure out the force on an area. So we took an area this way. Now, if I had taken an area this way, we would need to figure out force on this from this side or from this side. So we would need to figure out this force, and we can't figure out this force. So this would be not a good strategy. We took an area horizontally, so we can actually work out this weight. We can figure out this force, we can figure out. And that's what led to that force will be just the weight of the air above it and weight of the water. And then when we add it up like this, and we get this answer. This is a common strategy. Some people just memorize this formula, but when you memorize this formula, you have a very high chance of missing it. Okay. All right. Let me erase and look at 2. 2 is a more interesting problem. Okay. This is a problem in which you can there is a air getting trapped here, and as you pour more and more, of course this the pressure increases here, and you know, this thing fills up a little bit and a little bit and a little bit, etc. At some point, this is the situation. This density is not necessarily water, but it can be any fluid. Okay, and this side is open. This is open to air, and we're supposed to find what's the pressure over here. Okay, so it's a static. So when you have a static situation, then if you look at a point here and a point here, you will see the pressure will be the same on the 2 sides, and we can actually prove that, you know. So at this level the pressure is the same. So if I look at what's going on this side, a point here and a point here, there is a pressure of all of this and all of this. So over here, point A and point B, and over here is just the pressure of this guy is acting. So I'm going to just look at the area, both sides may be same. So area on the left side and area on the right side, and if they're equal, I'm going to write the formula and then you might cancel it later. So I have weight of air plus AL times AL times H times rho times G on the left side over area on the left is equal to it's just pressure here. I don't have I can just use the pressure which we want. So pressure acting over this area will be the force. Pressure acting over that area will be the force, and divide by AR. Okay, this is what we want. The area cancelled out, and so pressure that we want, pressure on the right side, will be just this will be the atmospheric pressure, and AL cancel out, and you get rho GH. So that's the answer. That's the answer of the pressure in the trapped, because it has to when you open this up, you would see as a consequence of this, suppose I have a U tube of any shape. So maybe this is thinner U and that side is much wider, but as long as the freely flow, the level on this side will match the level. If this is open and this is open, then the levels will always match. But if you close one of the levels, if you close one of the levels, one of the sides, then the levels don't have to match. So as you're filling in, say over here, as you're filling in, maybe it's matching here to here, but you fill in more, and you only go a little bit here because you're compressing this air now, and the pressure is no longer atmospheric pressure, and this is the extra pressure that must develop on this side to match on the both sides. Okay, this is kind of a important problem, and a lot of problems you will encounter, you will have to set things up like that. So the strategy here is to figure out, you figure like this. So the rule is this, rule for YouTube, okay, that you might use: both sides open, then same the bottom fluid, okay. So if it's one fluid, same, both sides open, same fluid. So I'm not using two different fluids, and I'm using two different densities. Same fluid will mean same level on both sides. If one side is closed, one side closed, another side open, same fluid again, levels will differ. Levels may differ, as in this example. Now, third example that you might have encountered is both sides open, different fluids. Not same level. Okay, so I'm going to erase this, and I'm going to actually do another video for this case. This case is what shows up a lot in the problems and is probably worth doing in a different video. Okay, so I will see you in another video. Don't forget to put a like it video or something like that, or if you want to check more out, it's going to be in this website. Okay, talk to you later in a video. Bye.